Hi, dear students. Coming to the last part of module 1 of data mining and data warehousing. We are going to discuss measures, their categorization and computation, and the last part we are going to discuss typical OLAP operations. So now, measures, their categorization and computation. So how measures are computed? So how measures are computed? To answer this question, we first study how measures can be categorized. Note that a multi-dimensional point in the data cube can be defined by a set of dimensions, dimension value pairs. How we define? A multi-dimensional point in a data cube space can be defined by a set of dimension value pairs. For example, time equal to Q1, that is I am taking the first quarter, and location equal to 1 cover, and item equal to computer. So now here I am going to find out how many number of computers are sold in a city called as Vancouver during the first 3 months, January, February and March. So this is a multi-dimensional point. Okay, a data cube measure is a numeric function. What is a data cube? What is a measure? A data cube measure is a numeric function that can be evaluated at each point in the data cube space. A measure value is computed for a given point by aggregating the data corresponding to the respective dimension value pairs, defining given point. We look at the concrete examples of this in this video lecture. So measures can be organized into 3 different categories. So one is distributive, another is algebraic, and the holistic, based on the kind of aggregation functions used. So based on which type of aggregated function are used, so the measures can be organized or classified into 3 categories. So one is distributive, another is algebraic, and one more is holistic. Okay, distributive function. Coming to the first one, distributive. An aggregate function is distributive if it can be computed in a distributed manner. What it says? An aggregate function is distributive if it can be computed in a distributed manner. For example, suppose the data are partitioned into n sets. We apply the function to each partition, resulting in n aggregate values. So what we are having? We are having a data which is partitioned to n sets. Now we apply the function to each partition, resulting in an aggregate value. If the result derived by applying the function to the n aggregate values is same as that derived by applying the function to the entire set without partitioning, the function can be computed in a distributed manner. For example, so that is one. If the result derived by applying the function to n aggregate values is same as that derived by applying the function on all the data set without partitioning, then that type of measure is called as a distributive measure. For example, sum. Sum can be computed for a data cube by first partitioning the cube into a set of subcubes. Now what we are doing, take a subcube, divide that subcube into a set of, divide that cube into a set of subcubes. Then compute sum for each of the subcube. Then summing up the count obtained for each subcube. Hence sum is a distributive aggregate function. So sum is a distributive aggregate function. For the same reason, the counts min and max are also distributive aggregate functions. By treating the count value of each non-empty base cell as 1 by default, count of any cell in a cube can be viewed as the sum of count values of all its corresponding child cells in the subcube. Thus, count is also a distributive. A measure is distributive if it is obtained by applying a distributive aggregate function. Distributive measures can be computed efficiently because of the way the computation can be partitioned. Next, coming to the one more type of measure called as algebraic measure. An aggregate function is algebraic if it can be computed by an algebraic function with m arguments. An algebraic if it can be computed by algebraic function with m arguments, where m is a bounded integer, each of which is obtained by applying a distributive aggregate function. For example, average. Can be computed by sum divided by count. How we calculate the average? Average can be computed by sum divided by count, where both sum and count are distributive aggregate functions. Similarly, it can be shown that minimum of n and maximum of n, which are standard deviations, are also algebraic aggregate function. A measure is algebraic if it's obtained by applying the algebraic aggregate function. Next, coming to the last type of measure, that is an holistic. Now, if there is no constant bound on the storage size needed to describe a sub-aggregate, then that type of approach or that type of measure is called as an holistic. Example, median, mode and rank. An aggregate function is holistic if there is no constant bound on the storage size needed to describe a sub-aggregate. That is, there does not exist an algebraic function with m arguments. Here, there is no algebraic function with m arguments where m is the constant that characterizes the computation. So, the common example of holistic functions include median, mode and rank. A measure is holistic if it is obtained by applying the holistic aggregate function. Most large data cube applications require efficient computation of distributive and algebraic measures. Many efficient techniques for this exist. In this contrast, it is difficult to compute holistic measures efficiently. Efficient techniques to approximate the computation of some holistic measures, however, do exist. For example, rather than computing the exact median value for a large data set, in many cases, such techniques are sufficient to overcome the difficulties of efficient computation of holistic measures. Now, coming to the typical OLAP operations, the last point in module 1. typical OLAP operations. What are the typical OLAP operations available? Typical OLAP operations includes roll up, drill down, slice, pivot. Okay. So here you see an example of a typical OLAP operations on multi-dimensional data. So this is a multi-dimensional data, and this table contains the item types, this contains the location cities, whereas this is also contains the location cities, and this is location with respect to countries, and this is the item types, and this is also an item types. Here we have cities, here we have months, and in this side we are having the item type. So how are concept hierarchies useful in OLAP? In a multidimensional model that are organized into multiple dimensions, and each dimension contains multiple levels of abstraction defined by a concept hierarchies. This organization provides users with the flexibility to view data from different perspectives. A number of OLAP data cube operations exist to materialize these different views, allowing interactive querying and analysis of the data at hand. Hence, OLAP provides a user-friendly environment for interactive data analysis. Let us come to the different OLAP operations. Let us look at some typical OLAP operation for a multidimensional data. Each of the following operations described is shown in figure 9. At the center of the figure is a data cube for all electronic sales. The cube contains, this cube contains the dimensions. What dimensions it contains? One is location, another is time, and item, where this location is aggregate with respect to the city values. The locations we are taking with respect to the city values. Time is aggregated with respect to the quarters, Q1, Q2, Q3 and Q4, and item is aggregated with respect to the item types. To aid in our explanation in this, we refer to this cube as a central cube. This is what? This cube is the central cube. The measure displayed is the measures whatever we are considering over here is the dollar sold in thousands. Now let us come to the first typical operation, OLAP operation, is the roll up. The roll up operation is also called as drill up operation by some vendors, which performs aggregation on a data cube either by climbing up a concept hierarchy for a dimension or by dimension reduction. Okay, roll up is like a zooming out onto a data. This is required when user needs further abstraction or less detail. Initially, a location hierarchy was street, city, province, country. On rolling up, the data is aggregated by the ascending location hierarchy from level of city to level of country. Okay, so how hierarchy is defined over here? So now here the hierarchy was defined by the total order street, city, province and country. Now the roll-up operation aggregates the data by ascending the location hierarchy from the level of city to the level of country. Now here you see, here we are considering in this dimension table we are considering cities. Now roll up, now we are going to get a data with respect to the countries like USA, Canada. Now here we have cities like Chicago, New York, Toronto and Vancouver. Now here we are taking into consideration USA and Canada at a higher level. In other words, rather than grouping the data by city, the resulting cube groups the data by country. So here you have grouped the data according to the cities, and here in this table we have grouped the data according to the country. When roll-up is performed, we are moving from a lower level to the higher level. So when a roll-up is performed by dimension reduction, the dimension reduction is done. How? We are moving from cities to the more hierarchical operation, that is the country. When roll-up is performed by dimension reduction, one or more dimensions are removed from the given cube. For example, consider the sales data cube containing only location and time dimension. Roll-up may be performed by removing, say, time dimension, resulting in an aggregation of total sales by location rather than total sales rather than location and by time. Now total sales with respect to the location. Now we are going to reduce by location and by time. Now coming to the drill down operation. So this is roll up is from lower level to the higher level, and drill down is from higher level to the lower level. Roll up is zoom out, whereas drill down is like zooming in into the data. This is reverse of the roll up. Drill down is the reverse of roll up. It navigates from the less detailed data to the more detailed data. Now you can see. So here, the less detailed data, we have the data with respect to the time is Q1, Q2, Q3, means only with respect to the quarters of an year. Now here we have data with respect to the every month. Instead of considering only 4 quarters, we have taken every month of an year. This is more detailed than this data. Drill down can be realized by either stepping down a concept hierarchy for a dimension or introducing additional dimensions. Drill down operation performed on a central cube, whatever we are performing over here, by stepping down a concept hierarchy from a time defined by the day, month, year, quarter. Drill down occurs by descending in the time hierarchy from the level of quarter to the more detailed level of the month. So that is only from quarter level we are moving to the month level. The resulting data cube details the total sales per month. So now here we are having the total sales in one quarter. So here we will be having total sales per month, summarizing them by the quarter. Because a drill down adds more detail to the given data, it can also be performed by adding new dimensions to a cube. For example, a drill down on a central cube can occur by introducing an additional dimension such as customer group can also be added. Next, coming to the slice operation. So before going to the slice, okay, let us go to the pivot or rotate. So here we are performing a pivot or a rotate. Pivot, this is used when the user wishes to reorient the view of the data cube. This may involve swapping the rows and columns or moving one of the row dimension into column dimension. Pivot, also called as a rotate, is a visualization operation that rotates the data axis in view to provide an alternative data presentation. So now what we have done. Now before, here on the y-axis you have cities defined, and on the x-axis you have the item types included. Now when you perform pivot, now on the y-axis you will have item type, and on the x-axis you have location defined. Okay, shows that is what a pivot operation shows. A pivot operation where the item and location axis in 2D slice are rotated. Other examples includes rotating the axis in a 3D cube also. or transforming a 3D cube into a series of 2D planes, also an example of a pivote. Now coming to the slice or dice. The slice operation performs a selection on one dimension of a given cube, resulting in a subcube. Now slice, slice, a part of any object we call as a slice. Slice operation performs a selection on one dimension of the given cube, resulting in a subcube. Okay, so now what is a slice? Slice from a higher dimension to the lower dimension. A part of the data I am taking. What part I am taking? Only, so here you have city, location, item and time. Out of that I am taking slice. What I am taking? Only location and item. I am excluding the time. That is the slice operation, where the sales data are selected from the central cube. For example, from this central cube, dimension, time using the criteria Q1. Okay, so now we are taking the slice, we are only taking a part of it. Now the dice operation defines a subcube performing a selection on 2 or more dimensions. Okay, so now dice operation. Now here, dice operation. Now what we have done in a dice operation, only a part, only one location with respect to city, and only 2 quarters Q1 and Q2 I am taking, and I am taking the item home, entertainment and computer, whereas security and cell phones are eliminated. I am taking only 2 cities, Toronto. Okay, I am taking only 2 cities, Toronto and 1 cover, where I am excluding New York and Chicago. So I am excluding, so out of these 4 quarters I am excluding Q3 and Q4, I am taking only Q1 and Q2. So I am taking home, entertainment and computer, I am excluding phone and security. So that is dice. Okay, these are the operations for placing data into the cube. These operations allow ability to look at the information from different viewpoint. A slice is a subset of the cube corresponding to a single value for one or more member of dimension. A dice operation is done by performing a selection of 2 or more dimensions. So here, what we have done, okay, so out of the 4 quarters I am taking only 2 quarters, out of the 4 cities I am taking only 2 cities, out of the 4 items I am taking only 2 items. That is a dice operation. Okay, so some of the other typical OLAP operations, some OLAP system offers additional drilling operations. For example, drill across executes queries involving more than one fact table. Drill through operation uses relation SQL facilities to drill through the bottom level of a data cube. Other OLAP operations may include ranking the top n or bottom n items in a list, or as well as computing moving averages, growth rates, interests, internal return rates, depreciation, currency conversion and statistical functions. OLAP offers analytical modeling capabilities, including a calculation engine for deriving ratios, variance and so on. And for computing measures across multiple dimensions, it can generate summarizations, it can generate aggregations and hierarchies at each granularity level and every dimension intersection. OLAP also supports functional model for forecasting, trend analysis and statistical analysis. In this context, an OLAP engine is a powerful data analysis tool. So that ends the module 1. So in this video lecture, we studied different measures, their categorization and computation. Different measures include distributive, algebraic, holistic, and we discussed different typical OLAP operations. One is roll up, which is like zooming out. Drill down is like zooming in, and then we studied rotate or pivot operation, which is rotating operation to reorient the data cube, slice or dice. Slice is a subset of a cube corresponding to a single value for one or more member of dimension, whereas a dice operation is done by performing a selection of two or more dimensions. So with this video lecture, we come to the end of module 1. So if you have any queries, you can post me on the YouTube, or you can personally WhatsApp me so that I can resolve your queries. So with this, we come to the end of module 1. Thank you one and all.